On July 23, 1999, the Space Shuttle Columbia blasted off from the Kennedy Space Center, carrying the Chandra X-ray Observatory. In the 2 decades that have passed, Chandra's powerful and unique X-ray eyes have contributed to a revolution in our understanding of the cosmos. To commemorate Chandra's 20th anniversary of science operation, a collection of new images representing the breadth of Chandra's exploration was released. These images demonstrate the variety of objects Chandra studies, as well as how X-rays complement the data collected in other types of light. Chandra is one of NASA's great observatories, along with the Hubble Space Telescope, Spitzer Space Telescope, and Compton Gamma Ray Observatory. It has the sharpest vision of any X-ray telescope ever built. Chandra is often used in conjunction with telescopes like Hubble and Spitzer that observe in different parts of the electromagnetic spectrum, and with other high-energy missions like XMM Newton and NASA's NuSTAR. Chandra's discoveries have impacted virtually every aspect of astrophysics. For example, Chandra was involved in a direct proof of dark matter's existence. It has witnessed powerful eruptions from supermassive black holes. Astronomers have also used Chandra to map how the elements essential to life are spread from supernova explosions. Many of the phenomena Chandra now investigates were not even known when the telescope was being developed and built after first being proposed to NASA in 1976. For example, astronomers now use Chandra to study the effects of dark energy, test the impact of stellar radiation on exoplanets, and observe the outcomes of gravitational wave events. The Chandra X-ray Observatory was named in honor of the late Nobel laureate Subrahmanyan Chandrasekhar. NASA's Marshall Space Flight Center manages the Chandra program. The Smithsonian Astrophysical Observatory's Chandra X-ray Center controls science and flight operations from Cambridge, Massachusetts. In 2018, NASA awarded a contract extension to continue operation and science support of Chandra through 2024, with the possibility of 2 3-year options.
Where do most of the elements essential for life on Earth come from? The answer: inside the furnaces of stars and the explosions that mark the end of some stars' lives. Astronomers have long studied exploded stars and their remains, known as supernova remnants, to better understand exactly how stars produce and then disseminate many of the elements on Earth and throughout the cosmos. Cassiopeia A, or Cas-A for short, is one of the most intensely studied of these supernova remnants. A new image from NASA's Chandra X-ray Observatory shows the location of different elements in the remains of the explosion: silicon, sulfur, calcium, and iron. Each of these elements produces X-rays within narrow energy ranges, allowing maps of their location to be created. Astronomers also see the blast wave from the explosion in the form of the blue outer ring. X-ray telescopes, such as Chandra, are important to study supernova remnants and the elements they produce, because these events generate extremely high temperatures, millions of degrees, that remain even thousands of years after the explosion. This means that many supernova remnants, including Cas-A, glow most strongly at X-ray wavelengths that are undetectable with other types of telescopes. Chandra's sharp X-ray vision helps astronomers not only determine what elements are present in Cas-A, but also how much of each there is. For example, Cas-A has dispersed about 10,000 Earth masses worth of sulfur alone and about 20,000 Earth masses of silicon. The iron in Cas-A weighs about 70,000 times that of the Earth, and astronomers detect a whopping 1 million Earth masses worth of oxygen being ejected into space from Cas-A, equivalent to about 3 times the mass of the Sun. Chandra has repeatedly observed Cas-A since the telescope was launched into space in 1999. It will continue to do so, revealing new information about the dense core left behind in the center of Cas-A, details of the powerful explosion, and specifics of how the important debris is ejected into space.
The Crab Nebula was one of the first objects that Chandra examined with its sharp X-ray vision, and it has been a frequent target of the telescope ever since. There are many reasons that the Crab Nebula is such a well-studied object. For example, it is one of a handful of cases where there is strong historical evidence for when the star exploded. Having this definitive timeline helps astronomers understand the details of the explosion and its aftermath. In the case of the Crab, observers in several countries reported the appearance of a new star in 1054 AD in the direction of the constellation Taurus. Much has been learned about the Crab in the centuries since. Today, astronomers know that the Crab Nebula is powered by a quickly spinning, highly magnetized neutron star called a pulsar, which was formed when a massive star ran out of its nuclear fuel and collapsed. The combination of rapid rotation and a strong magnetic field in the Crab generates an intense electromagnetic field that creates jets of matter and antimatter moving away from both the north and south poles of the pulsar. Astronomers also see an intense wind flowing out in the equatorial direction. A new composite image adds to a scientific legacy spanning nearly 2 decades between Chandra and the Crab Nebula.
This image from the Chandra X-ray Observatory reveals a wealth of exotic objects and high-energy features at the center of our Milky Way galaxy. In this new and deep image from Chandra, red represents lower energy X-rays, green shows the medium range, and blue indicates the higher energy X-rays Chandra can detect. The hundreds of small dots show emission from material around black holes and other dense stellar objects like neutron stars. A supermassive black hole, some 4 million times more massive than the Sun, resides within the bright region to the right of center. The diffuse X-ray light comes from gas heated to millions of degrees by outflows from the supermassive black hole, winds from giant stars, and stellar explosions. This sequence begins with an infrared view from the Spitzer Space Telescope of the central region of the Milky Way. We then zoom into a region about 1.4 degrees away from the center of the galaxy, where the Chandra X-ray Observatory focused its attention for about 12 days worth of time. This region is known as the Galactic Ridge, because earlier X-ray observatories found a structure of diffuse emission stretching across the plane of the galaxy. The new long Chandra observation shows that this X-ray haze is actually composed of thousands of individual sources like stars and binary systems.
Astronomers have discovered evidence for thousands of black holes located near the center of our Milky Way galaxy, using data from NASA's Chandra X-ray Observatory. This black hole bounty consists of stellar mass black holes, which typically weigh between 5 to 30 times the mass of the Sun. These newly identified black holes were found within 3 light-years, a relatively short distance on cosmic scales, of the supermassive black hole at our galaxy's center, known as Sagittarius A star. A black hole by itself is invisible. However, a black hole, or neutron star, locked in close orbit with a star, will pull gas from its companion. Astronomers call these systems X-ray binaries. This material falls into a disk and heats up to millions of degrees and produces X-rays before disappearing into the black hole. Some of these X-ray binaries appear as point-like sources in the Chandra image. A team of researchers determined that a dozen of the point sources in the Chandra field of view contained a stellar mass black hole. By combining this result with theoretical modeling, the scientists think that up to 1,000 of these black holes could be present around Sagittarius star. This population of black holes, with companion stars near Sagittarius star, could provide insight into the formation of X-ray binaries from close encounters between stars and black holes. This discovery could also inform future gravitational wave research. Knowing the number of black holes in the center of a typical galaxy can help in better predicting how many gravitational wave events may be associated with them.
Astronomers have long known that the supermassive black hole at the center of our Milky Way galaxy is a particularly poor eater. The fuel for this black hole, known as Sagittarius A star, or Sag-A star for short, comes from powerful winds blown off nearby stars. Scientists have previously calculated that Sag-A star should consume about 1% of the fuel carried in these winds. However, it now appears that Sag-A star consumes much less than even that. It only ingests about 1% of that 1%. Why does it consume so little? A theoretical model based on these new deep data seen in this Chandra image may provide the answer. It turns out that there is an inner and outer region around the black hole. Pressure flowing outward causes nearly all of the gas to move away from the black hole. This, in turn, starves the black hole of much of its fuel, and this is why astronomers have seen so little activity from this, our closest supermassive black hole.
Many consider Andromeda, also known as Messier 31, to be a sister galaxy to our own Milky Way. At a distance of only 2.5 million light-years away, Andromeda is relatively close to our galaxy. It is also a spiral galaxy, like the Milky Way, and has many similar characteristics. However, a new study using data from NASA's Chandra X-ray Observatory has pointed out some interesting differences between these two galaxies when it comes to black holes. After combining over 150 Chandra observations spread over 13 years, researchers discovered 26 new black hole candidates in Andromeda. This is the largest number to date found in a galaxy outside our own. Falling into the stellar mass category, these black holes form when the most massive stars collapse. The result is a black hole that typically has between 5 and 10 times the mass of the Sun. 7 of these black hole candidates are within 1,000 light-years of Andromeda's center, more than what is found near the center of our Milky Way's core. This highlights that although Andromeda and the Milky Way are alike in many ways, they do have their differences. Astronomers have long known that the bulge of stars in Andromeda is bigger, as is the supermassive black hole at its center. Now, we know that it may be a better producer of small black holes as well.
Earlier this year, astronomers discovered one of the closest supernovas in decades. Now, new data from NASA's Chandra X-ray Observatory has provided information on the environment of the star before it exploded and insight into the possible cause of the explosion. On January 21, 2014, astronomers witnessed a supernova just days after it went off in the Messier 82 or M82 galaxy. Telescopes across the globe and in space turned their attention to study this newly exploded star. Astronomers quickly determined this supernova, dubbed SN 2014J, belongs to a class of explosions called Type 1a supernovas. These supernovas are used as cosmic distance markers and played a key role in the discovery of the universe's accelerated expansion, which has been attributed to the effects of dark energy. While astronomers agree that Type 1a supernovas occur when a white dwarf star explodes, they are not sure exactly how this happens. For example, do these supernovas go off when the white dwarf pulls too much material from a companion star like the Sun, or when two white dwarf stars merge? Researchers used Chandra to look for clues. They took observations with Chandra about 3 weeks after 2014J and compared it with Chandra data taken prior to the explosion. They found, well, nothing. Although it may sound counterintuitive, this non-detection of X-rays actually told astronomers quite a bit. Specifically, it showed that the environment around the star was relatively free of material before it exploded. This means that it's very unlikely that a messy transfer of material between the white dwarf and a companion star took place. Rather, whatever caused SN 2014J to explode cleared out the space around the star beforehand. This helps astronomers narrow down the possibilities and get closer to the answer of just what caused SN 2014J.
Dark matter is the mysterious and pervasive substance that constitutes most, about 85%, of the matter in our universe. Although scientists have made progress in better understanding dark matter, the true nature of this invisible material remains elusive. NASA's Chandra X-ray Observatory plays an important role in the search to learn about dark matter. One way that astronomers have used Chandra to investigate dark matter has been through the study of a mysterious signal seen in X-ray data. In 2014, astronomers reported they found a spike of intensity at a very specific energy in Chandra and XMM Newton observations of the hot gas in the Perseus and other galaxy clusters. This spike, or emission line, is at an energy of 3.5 kiloelectron volts, or keV, and could not easily be explained as emission from known elements. Therefore, one possibility was that this line was produced by dark matter particles. Naturally, determining the true nature of dark matter would be a huge discovery, and as Carl Sagan famously said, extraordinary claims require extraordinary evidence. Therefore, astronomers have been working hard both to replicate the initial results and also provide explanations for all of the observations connected to this original finding. Now, a new team of astronomers has provided an innovative interpretation of the observations surrounding this 3.5 keV line. They propose that there is another mechanism at work, namely the absorption of X-ray light by mystery particles. If this is true, then it's possible that the 3.5 keV line may, in fact, be produced by dark matter particles. While these ideas need to be confirmed with future observations, it may be that the prospect of determining the nature of the darkest of matter may never have been more bright. A team of astronomers has used NASA's Chandra X-ray Observatory and ESA's XMM Newton to study a large group of galaxy clusters with a surprising result. Galaxy clusters are the largest objects in the universe held together by gravity, and thus can reveal lots of information about the cosmos. This most recent study, which included the well-known Perseus cluster and 72 others, has uncovered a mysterious X-ray signal. Astronomers are intrigued by a spike of intensity at a specific wavelength of X-ray light in the data because of one proposed explanation. Scientists think that a hypothetical particle, called a sterile neutrino, may in fact be responsible for this spike of intensity. Some scientists have proposed that the sterile neutrino could be a candidate for dark matter, something that makes up about 85% of the universe, yet does not emit or absorb light. While they are excited about this finding, the researchers say it's too early to claim whether or not this mysterious X-ray signal is real, or whether or not it is indeed the signature of the sterile neutrino. They'll keep gathering data and looking at other galaxy clusters to make sure they see it elsewhere. In the meantime, they'll be looking at their theories to see where else the physics may take them.
Many people have heard of auroras, also called the Northern Lights, which are spectacular light shows that occur near Earth's poles. What might not be as well known is that other planets in our solar system also experience auroras. Jupiter is one of them. A new study using data from NASA's Chandra X-ray Observatory has shown that storms from the Sun are triggering auroras in X-ray light that are some 8 times brighter than normal, covering a large area of Jupiter's surface. These Jovian auroras are hundreds of times more energetic than the auroras we have here on Earth. These latest results represent the first time that Jupiter's auroras have been studied in X-ray light when a giant storm from the Sun arrives at the planet. The Sun constantly ejects streams of particles into space in the solar wind. Sometimes giant storms erupt and the winds become much stronger. These events compress Jupiter's magnetosphere, the region of space controlled by Jupiter's magnetic field, shifting its boundary with the solar wind inward by more than 1 million miles. This new study found that the interaction at the boundary triggers the X-rays in Jupiter's auroras, which cover an area bigger than the surface of the Earth.
During the summer of 2015, scientists and the public alike were treated to a flood of images and discoveries about Pluto as the New Horizons spacecraft made an unprecedented flyby of the dwarf planet. The discoveries about Pluto didn't stop with the initial results that were released. Rather, the New Horizons spacecraft will provide scientists with years' worth of discoveries of this cold and distant world. While New Horizons is accomplishing much on its own, there is even more science to be uncovered when other telescopes join the effort. This is the case for X-ray observations of Pluto made by the Chandra X-ray Observatory as New Horizons made its approach and then flew by Pluto. The Chandra data show that Pluto has surprisingly high amounts of X-ray emission for a cold and rocky planet that has no known significant magnetic field. While X-rays have been detected elsewhere in the solar system, including comets, Mars, Saturn, and Jupiter, it appears that Pluto's X-rays are not generated in exactly the same way as these other objects. Rather, the researchers suggest that the X-rays from Pluto come from the interaction of gases in Pluto's atmosphere and the stream of particles from the Sun, known as the solar wind. Scientists hope to learn more about Pluto and other objects in the outermost regions of our solar system with future observations.